Hello, good morning, good afternoon, and good evening wherever you are. Welcome to the SNIA Networking Storage Forum, or NSF webcast, about the new landscape of network speeds. I am your host, John Kim, and I'm happy to have four great presenters today, including myself. So let's get started. We have a lot of great content, and I want to go ahead and jump into it as soon as possible. Today's presenters are David Chalupsky from Intel, Craig Carlson from Marvell, Peter Onufryck from Microchip, and myself, John Kim, from Mellanox, also chair of the SNIA NSF. Two brief slides about SNIA. SNIA is a great organization, a leading group on storage and storage networking. We have more than 185 industry-leading organizations, more than 2,000 active contributing members, and more than 50,000 total members and viewers around the world. You can learn more at snia.org/technical or follow us on Twitter @SNIA. Just a brief legal disclaimer and notice. The material here in this presentation is copyrighted by SNIA unless otherwise noted. Member companies are free to use this material as long as they acknowledge the source of it. The presentation is a project of SNIA, and neither the nor any of the presenters in this webinar are attorneys, and nothing in this presentation is intended to be or should be construed as legal advice or opinion of counsel. The information presented herein represents the authors or presenters' personal opinions and current understanding of the relevant issues and technologies involved. No warranties expressed or implied. Use this material at your own risk, but that said, we do believe it's pretty interesting and fairly accurate. So today's agenda is new trends in networking speeds. We'll cover Ethernet, then Fibre channel, then PCI Express, then InfiniBand, and we'll have a brief discussion about what it all means. We invite you to ask questions at any time. You can ask online, and then we will answer as many as we can during the webcast. Any questions we don't get to, we post it in an FAQ usually about a week after the webcast. All right, and we will post the slides of this webcast online right after the webcast. So brief question before we get started is, why do people need faster networking? Why are we developing all these faster speeds? And part of it is that the servers are getting faster. There are more and faster CPUs. There are more GPUs. There are more FPGAs. There are smarter NICs and basically faster, smarter servers. And the storage is getting faster. So we have faster storage media, faster storage protocols like NVMe over fabrics. And that all means faster servers want to get to that storage more quickly. We also have an uptick in 4K and 8K video. So whether it's streaming or digital cinema or the upcoming Olympics, which are supposed to be done in 8K video, there's just more and more high-resolution video that requires fatter pipes to get that video to the right place where it needs to be. And finally, we're seeing that big data centers, whether it's cloud or large enterprise, they want wider pipes. They need bigger and ideally fewer links between their switches or across the data centers, and these bigger, faster connections allow them to build a more efficient fabric. So that said, let me turn it over to David Chalupsky to start off with Ethernet. Dave?
Well, thank you, John. Here we go. There's the forward button. In the Ethernet section, we're going to talk about speeds and a little bit about PHY types, and especially we're going to look at the applications that Ethernet has grown into over the years. As John mentioned, there's a lot of applications driving higher and higher speed networking, but there's also some different applications driving some different speeds and some different flavors of connectivity that are of interest. And I'd like to thank the Ethernet Alliance for all the graphics that I'm about to use here. You can find this on the Ethernet Alliance's website, ethernetalliance.org, and these pictures come from the Ethernet Roadmap. So, first question about speeds. If you've been following the history of Ethernet, which was first invented back in the 70s and became an IEEE standard in the early 80s, in the first 30 years of Ethernet history, we had developed 6 speeds from 10 megabit, 100 megabit, 1 gig, 10 gig, and then together 40 and 100 gig. And then all of a sudden, there was a bit of an explosion in new Ethernet speeds. And in the next next few years, 6 new speeds were all developed at one time. And we'll see that driving all these speeds, both higher and lower, came from a variety of different applications where Ethernet was becoming used. And when I say we, it wasn't just John and myself developing this. This was primarily IEEE's 802.3 working group is the source of Ethernet standards. So what started back in the 70s as one of the early local area network technologies, back in the day, the application was to connect a computer to a printer, and there were several competing LAN technologies in the 70s and 80s, and over the decades, Ethernet has sort of won the market for Ethernet, or for local area networks. It's used in a variety of areas. Of course, it's very common as the corporate LAN. It's wireless backhaul, it's data center interconnect, and storage fabric. So let's look at some of these application areas in depth. This pretty, though eye-chartish picture here comes from our Ethernet roadmap from the Ethernet Alliance, basically calling out 5 different application areas that are driving evolutions in Ethernet. Now, I'm not expecting you can see the detail in this picture, though you can find it on the EA's website, but we're going to take each area separately. So starting from the left of that little pie chart there, we see the field of automation, building automation, industrial controls, controlling elevators. This would be the categories we call the Internet of Things. So Ethernet speeds and reaches here, the speeds are not terribly high, especially in control areas or a thermostat or controlling lighting. The data rates aren't terribly high in many of these applications, although some of them, like cameras, are driving higher speeds. What's more useful is reaches that can go from a few meters up to a kilometer, and also some of the copper-based physical internet Ethernet also have the ability to carry power over the same wires that are delivering the data. That's very useful for remote equipment, such as a thermostat or a wireless access point that can be powered over the same line you're getting data. Now, moving to the next area, this is one of the newer areas for Ethernet to be penetrating, but over the past few years, Ethernet has been becoming used in automobiles. Probably the first use here was a 100 megabit Ethernet non-standard PHY that automakers and one PHY supplier developed. And since then, the interest in the automotive OEMs in Ethernet has been growing so much that there's been several automotive Ethernet projects and standards developed, starting with 100 megabit, then 1 gigabit, and there's currently going both slower and faster. So there's currently a 10 megabit project that is automotive and industrial focused, and also a multi-gig project that is doing 2.5, 5, and 10 gig, and actually just starting out now this week in IEEE is a greater than 10 gigabit project that will be targeting most likely 25 and perhaps even 50 gigabits per second. So what's the demands of this application here is not only the wide variety of speeds, you can imagine with all the different control points and sensor points in vehicles, that the data rates are very, very different. Running a door lock is not the same as what we need out of a camera or mapping, etc. So these are fairly short domains, of course. So these automotive-focused PHYs run up to 15 meters. And again, we have the great feature of being able to deliver power over the data lines. As these are being developed, they know that they're in a very rugged, high temperature, low temperature, and EMC, or electromagnetic compatibility environment. So the PHYs are specifically designed to be used in those environments. And also a key attribute here is this whole family of PHYs runs on a single pair of copper wires. So the wiring harness in a vehicle to be one of the heavier components in a car, just behind the engine transmission. The wiring harness can add a significant amount of weight. So getting all the onto a single pair of wire has been a big focus in the automotive world. Moving on next to, click. Now the more well-known, perhaps, application for Ethernet, really one of its original applications, was in the enterprise campus and the enterprise center. So for decades, we had Ethernet wired into our corporate buildings and office buildings, and that continues today. Although a lot of end users actually now connect over Wi-Fi, we still see that Ethernet is almost ubiquitously used as the uplink from the Wi-Fi access point into the corporate network. So this gives us reaches of tens to hundreds of meters, speeds still from 100 megabit up to 100 gigabit in the data center. Again, especially for the wireless access point or phones, we see the use of power over Ethernet, and kind of one of the hallmarks of this style of networking. Primarily, this is the 45, the base T family, and just ease of use, ease of installability, ease of migrating speeds from one generation to the next, and being able to reuse infrastructure. In fact, this is one of the more recent developments over the last few years, was developing 2.5 and 5 gig, as I mentioned early on, drivers to go both faster and slower. So it was a little bit unusual for those in the Ethernet world to see that people wanted to go slower and go down to 5 gig or 2.5 gig. But the driving factor there was that there's over 70 billion meters in the installed base of Cat5e and Cat6 cabling that are not capable of carrying 10 gig, but they are capable of carrying 2.5 and 5 gig. So we developed PHYs specifically for that to get more bandwidth out of existing cabling. Next, the cloud Hyperscale data center cloud service providers. This has been really the driver for high end in recent years. Within the data, we see reaches of, say, from just a couple of meters for servers in the rack connecting to a switch in the rack, up to about 500 meters and span across data centers. The warehouse size data centers are growing larger and larger, and we find that we need fairly long reaches just to run across the indoor data center. Of course, there's also data center interconnect and outdoor uses, which drive from 2 kilometers and now even up to 80 kilometers. This is another recent development within Ethernet standards. Is previously the longest reaches we'd done with Fibre in Ethernet had been 40 kilometers, and we're now developing 80 kilometer reaches for very long scale reaches. And again, your server interconnect here might be 10 gigabits today predominantly, and migrating up to 25. And then in the leaf design or in the data center interconnect, you see higher speeds all the way up to 400 gig now being deployed. And lastly, other service providers such as telecom, the wireless backhaul. So wherever you see a cell tower, there's something wired, of course, that is getting your phone connections back into the network, and more that's moving toward Ethernet. Internet exchanges are places where very high bandwidth, different networks connect together on a wide basis. So again, we see indoor reaches 2 meters to 500 meters, and the same outdoor reaches 2 kilometers to 80 kilometers, and speeds 10 to 400. So very similar need networking to the cloud providers. And I believe we're coming up to the end here. But we are in a storage discussion here, so I didn't really mention a lot about storage. But Ethernet.
David, sorry, this is John. If you could actually just slow down your presentation a little bit and speak, because we have some audio issues. I think it'll come through more clearly if you speak a little more slowly for the last few slides.
Okay. Got to combat the inter-symbol interference here from a bad connection. I lost my spot. Here we go. So it is also one of the common interconnects for storage, and we're going to hear about others, of course, in this webinar. But Ethernet has been used for quite some time as a storage interconnect as well. Just the concept of network-attached storage that you can map a drive on a server has been around for quite a few years. And also block-oriented storage, such as iSCSI and Fibre channel over Ethernet. And a newer development really getting traction here is NVMe over Fabric. which could be NVMe over RDMA and also NVMe over TCP, are new developments in Ethernet storage applications. So Ethernet has been an infrastructure for storage for some time, and new developments are going on there as well. So lastly, what about the speed roadmap for Ethernet? So we currently have standards completed and products being deployed all the way up to 400 gigabit Ethernet. And currently, within IEEE's 8.3, there's development on for that next basic building block, which is the ability to do 100 gigabits per second on a single lane or a single SerDes interface. And this project will probably take another year or so to complete. I don't have the date in front of me, but then that will become the basis of higher port speeds as well. We can use that basic 100 gig per lane, interconnect, taking it as a single lane at a time, or by 2, by 4, by 8, which will easily get us up to 800 gig networking. And then technology development work is already beginning in the 200 gigabit signaling realm as well. So you see here a trend that is not only in Ethernet, but in other communication protocols where this basic building block of a signaling path or a SerDes can be used one at a time, or by 2, by 4, by 16, to logically bind all those lanes together to act as one higher speed port. And that gives us the ability to do higher speed ports all based upon the same technology. And that's the end of our Ethernet section. Let's turn it over to Greg Carlson.
Thank you, David. And Craig, please go ahead. Craig, you might be on mute. We can't hear you.
Oh, sorry about that, John. Yes, I was on mute. Going all the way back to the beginning of fiber channel speeds here on this slide, and the standards that support it. Go all the way back to 1 gigabit fiber channel, which was the FCIA standard, which I think was developed around 1996, 97. All the way up to today, we have the FCIA 7 and PCIe standards. PCIe 7, which is the most recently completed standard, which defines 64 gigabit fiber channel, and PCIe 8, which is the standard now in development, which defines 128 single stream gigabit fiber channel. And to go along with that, we have the FCIA Roadmap, which shows these speeds going all the way back again to 1996, up to the current speeds, which are 128, 64 GFC and 128, 64 GFC was completed in 2017, 2018. Market availability starting this year. And 128 development is starting this year with market availability probably around 2020. The slide hasn't been updated to show that, but that's our expectation. And a little bit about the abbreviation. We use the GFC to specify the speed of 1 GFC, which is 1 gigabit fiber channel. It maps to these particular data rates on this slide. So 64 GFC maps to a 28.9 megabaud and a 6400 megabytes per second. We also have the different speeds which have 4 lane variants as well. So as I mentioned, FCIA 7, which is the 64 GFC, was just completed in mid-2018. And as always with fiber channel, we go back 2 speeds. We're backward compatible to 2 speeds. So this is backward compatible to 32 GFC and 16 GFC, which allows plug-and-play compatibility with existing infrastructure in the data center. Also compatible with existing cable assemblies as well. The reach goals are the same as we've had in the past, 100 meters for OHM 4, OHM 5 cable. OHM 3 cable is also supported at a shorter distance. And we also have 10 kilometers for single mode optical. And we also have a electrical variant as well. And as you would expect, 64 GFC does double the throughput of 32 GFC. And the way we get to a 64 GFC is, as with other technologies, we use a a forward error correction, which allows us to get a bit error rate of 1 to e-15. So forward error correction, and why am I making a big deal of this? Other technologies use this. 64GFC, for 64GFC, we made forward error correction mandatory for all links, and this includes both copper and optical links. This allows us to use the redundant coding to correct errors in the data stream. And for those of you who might have an interest in what this is, it's something called a Reed-Solomon block code, and it allows a correction of a certain number of errors within a block of data. The uncorrected data rate is 1 e to the -4, and the corrected data rate is 1 e to the -15, which shows you what the FET can do to allow for this data rate. Another variant that we're developing in the standard FCPI7T is a 4-lane variant for 64GFC, which brings us to a 256 gigabit parallel variant. And this standard is currently in development. We expect the first approval process to start in mid-2019. And the way this works is it's striped across 4 lanes, and it has some of the similar characteristics of the single stream, which is 100 meters on multimode, OM4, OM5, with a 2 kilometer single mode variant. And as usual with Fibre Channel, it's backward compatible to the previous speeds, and we're backward compatible with 128, which is GFC parallel, which is 4x32. So what's new in Fibre Channel? What's coming up? We got PI8, which 128 GFC single stream. I mentioned the parallel stream, but this is a single stream, and FCNVMe2 is coming up as well. So 128 GFC, which is the FCPI8 project. As usual, backward compatible with 64 and 32. Uses the same or similar connectors, same connectors to 32 and 64. And existing cable assemblies will work up to 100 meters on OM4, OM5. And as usual, there's a shorter distance available on OM3. Single mode cable plan reach capability of 10 kilometers. And as usual, the 128 doubles the 64. Corrected bit error rate target is the same as before, is at 1 to the -15th. And we have a reduced latency goal of up to 20% over 64. And a 4-lane parallel variant is also in the works, which will bring us to 512 gigabit Fibre Channel. We've also been working on the second revision of FCNVMe. So FCNVMe is NVMe over fabrics mapped onto Fibre Channel. And the focus for the second variant, second revision of FCNVMe is on error recovery. We've put in place a mechanism to detect any errors at the transport level, which allows for quick error recovery, and such that the upper layers, the NVMe layer, really doesn't know that anything has happened. This adds to the already reliable nature of Fibre Channel to make it that much more reliable for the flash array data centers. And as I mentioned, what is the biggest use case? The biggest use case for these new speeds in Fibre Channel is really the all-flash array data center. And Fibre Channel with FCNVMe and now FCNVMe2 is very well positioned to support this. According to Gartner, current for deployments of all-flash arrays are about 70%, have about a 70% connection with Fibre Channel. FCNVMe was ratified in 2017, and FCNVMe2 is now on the way, as I mentioned. And this brings the same Fibre Channel enterprise capabilities to NVMe over fabrics, and it supports the existing services. I won't name them all here, but the existing Fibre Channel services which are supported in the other protocols, such as SCSI and FICRON. And that's all I have.
Craig, thank you. Actually, could you answer one question from the audience? The question is, for 100 gigabit per second signaling, the future standard, is it expected to work over copper cable, passive or active, or only optical? And I think the question is 100 gigabit second per lane, not the 4x32 or 4x25.
Yeah. So the answer to that is we will have. I mean, for the data center, you're going to be using optical. We do have a copper variant, which of course will be a much shorter distance for both passive and active. Passive most likely be for backplanes and things like that. Active would be for slightly longer. We're still in the definition stages of exactly what those copper variants will look like. But yes, there is a plan for that.
Right. And also for the Ethernet application of 100 gig signaling, the objective is to get to just a 2-meter reach on copper, and the use case there being servers within a rack. And if you physically locate your switch in the center of the rack, then a 2-meter reach will serve those servers in the rack, and then everything longer to get outside of the rack would be optical or active cables.
Thank you, Craig, and thank you, David. That's great. All right, let's move on to the PCI Express or PCIe section. Peter Onufryck, please take it away.
Okay, great. Thank you. So let's turn our attention now to PCI Express or PCIe. The PCI Express specification is defined by the PCI SIG, which is an industry organization chartered with maintaining PCIe-related specifications. PCIe works over serial links and is backwards compatible with the parallel PCI and PCIX I/O buses. This means that code written over 20 years ago for PCI and PCIX still works unmodified on PCI Express. PCI Express is high performance and scalable from consumer to enterprise applications. You'll find PCIe in everything from consumer devices such as laptops all the way up to things such as high-end servers and storage array. The primary application for PCIe is as an I/O interconnect. It is used to connect I/O adapters for things such as SAS, Fibre channel, Ethernet, and InfiniBand to a host CPU. So one application of PCIe is to connect the interfaces associated with the other networks in this webinar to a CPU. But as we'll see in a moment, PCIe itself can also be used as a storage network. One of the main drivers for using PCIe as a storage interconnect has been the development of NVMe Express or NVMe. NVMe is the interface used for direct attached PCIe SSDs. Prior to NVMe, there were PCIe SSDs, but to use one of these PCIe SSDs, you had to load a proprietary vendor-specific driver. NVMe changed all that by standardizing the PCIe SSD interface. So today, you can just plug in a PCIe SSD, and an OS inbox driver will load, allowing the SSD to just work, and there's no need to load a vendor-specific driver. The NVMe base specification, which you can download from nvmexpress.org, defines the architecture, command set, and queuing interface for PCIe SSDs. NVMe was architected from the ground up for high performance and is optimized for non-volatile memory. With the success of NVMe for PCIe SSDs, NVMe has now been extended to work over other storage networks, such as those described in this webinar. On the right are three of the most popular NVMe SSD form factors. M.2 drives are about the size of a stick of chewing gum and are mainly used in client applications and in server boot drives. U.2 drives are the size of a 2.5-inch hard drive and are typically used in servers. Finally, PCIe add-in cards allow an NVMe SSD to be plugged into a standard PCIe card slot. In addition to these form factors, there are a number of new emerging form factors under the EDSFF umbrella that we'll see in the coming years. While modern chipsets provide a lot of PCIe ports, there are some applications that require more PCIe SSDs than PCIe ports provided by a CPU. For these applications, we have JBOFs. A JBOF stands for just a bunch of flash and are just like JBODs, except they use flash-based SSDs instead of hard drives. It's possible to build a PCIe JBOF by putting a PCIe switch in an enclosure with a bunch of NVMe SSDs and cabling the enclosure to a server using PCIe. This is an example of the classic PCIe fan-out application. A logical representation of this is shown on the left. On the right, there's an actual example of a JBOF, which is the Facebook Lightning platform. As I previously said, PCIe fabrics are primarily used for fan-out applications, and a JBOF is an example of that. But PCIe fabrics can also be used to build more complex topologies. Two examples are shown on this slide. Using NVMe SSDs that support PCIe single root virtualization, or SRIOV, it's possible to build a PCIe fabric that allows the storage provided by those SSDs to be shared among multiple hosts. An example of this is shown on the left. Here we have NVMe SSDs, each of which implement 4 virtual functions. Using fabric-enabled PCIe switches, it's possible to map each of these virtual functions to a host. Each host sees just a bunch of NVMe drives and is able to access them using standard inbox drivers, so no software infrastructure changes are required. Traditionally, storage has revolved around providing storage access to a CPU. This could be direct attached or over a storage network, but the center of the universe has historically been the CPU. With the increased importance of accelerators and GPUs for applications such as AI, the CPU is no longer the center of the universe. However, memory is still typically attached and part of the CPU, requiring I/O to go in and out of the CPU, creating an I/O bottleneck. PCIe fabrics can be used to allow direct transfers between accelerators and storage. An example of this is shown on the right. In this example, we have hosts sharing NVMe SSDs with PCIe switches interconnected in a full mesh topology. In this PCIe fabric, we also have accelerators and network interfaces that can directly transfer data to storage, eliminating the CPU memory bottleneck. This slide shows the PCIe roadmap. The x-axis represents dates for when a specification was released, and the y-axis is relative performance of the highest link speed defined in that specification. One detail to note is that there are specification versions like PCIe 2.0 and PCIe generations used to denote link speed like Gen 2. Gen 2 is defined in PCIe 2.0, but it's possible to build a PCIe 2.0 compliant device that doesn't support the Gen 2 link speed. So there's link speed and specification version. In this graph, we can see that each specification generation doubles the performance, and that the specification cadence at the start was about every 3 to 4 years. Then we stopped at PCIe 3.0 for 7 years. Then starting at PCIe 4.0, we are at a specifications of every 2 years. PCIe 5.0 is expected to be ratified later this year, and the PCI SIG has started feasibility work on PCIe 6.0 and is targeting spec completion in 2021. So the rate of specification releases has accelerated, and this is causing PCIe performance to align back with the historical trend shown by the orange arrow. Now let's take a look at some PCIe technical characteristics. PCIe has a scalable speed from 2.5 gigatransfers per second to 16 gigatransfers per second today, and with a roadmap to 64 gigatransfers in the future. Each generation doubled the effective data rate. But you'll notice that Gen 2 is 5 gigatransfers, and Gen 3 is 8 gigatransfers, and 8 is not double 5. The reason the data rate doubled, even though the link speed didn't in this case, is due to an encoding change. So Gen 1 and 2 use 8B 10B encoding, while Gen 3 and beyond use 128-bit 130B encoding. If the performance of one PCIe lane isn't sufficient for an application, you can combine multiple PCIe lanes to create a wider port width. Unlike some other technologies, PCIe packets, called TLPs, are spread across the lanes of a port. So increasing port width not only improves throughput, but also reduces latency. Common port widths are shown in the bottom right of the slide. So by 1, by 2, by 4, by 8, and by 16 are very common port widths. By 12 and by 32 are allowed by the specification, but I've never actually seen anyone implement these port widths. There's an old saying in auto racing that goes something like, speed costs, how fast do you want to go? And this is true not only for auto racing, but it's also true for PCIe. As the link speed increases, the distance signals travel in a given board material decreases. On the right, I show the implication of this for a trace length that roughly corresponds to what you would see in a motherboard and an add-in card application. At Gen 4, a board material called MEG2 allows the signal to go about 15.5 inches. To go the same distance at Gen 5 requires you to use MEG6, which can increase the cost of a board by 25% or more. The situation gets even worse as we go faster with Gen 6 and beyond. There are a number of ways to increase signal distance. One could use more expensive board materials, as I just described. One could use a PCIe extension device, such as a PCIe retimer or a PCIe switch. One could use cables instead of board routing. Signals travel farther in cables. But regardless of which of these you choose, all of them increase system costs. So going faster will cost more money. Initial applications for the faster PCIe speeds will be applications that can actually benefit from those faster speeds. This will be things like high-speed networking, GPUs and accelerators, and NVMe SSDs that use next-gen NVM. So with that introduction to PCI Express, let me turn it over to John for InfiniBand.
Thank you, Peter. And actually, before we do that, there's a question, and let me know if you can answer it. The question is, any comments on why U.2 drives are so rare or uncommon in desktop PC usage? My M.2 seems very common in laptops and some desktops, but U.2 large capacity seems a better fit for a desktop. So I assume this question is specifically about U.2 NVMe drives, but I'm not sure. Peter, can you address that one?
Yeah, I mean, so M.2 are typically client drives, so they're lower cost, typically used in laptops and kind of appropriate for desktops. U.2 are typically used in server applications, so they're usually much higher capacity, have more features, and more expensive. So it's just natural that we wouldn't really see them in kind of client or desktop applications.
Okay, well, that certainly makes sense. Yeah, I could see it would be difficult these days to fit a U.2 drive into any of the slim laptops. But okay, let me go forward. Let me mark that question as answered. And again, for the audience, please keep the questions coming online, and we will answer as many as we can live, and any others will be answered, posted in an FAQ afterward. So great presentation so far from David, from Craig, from Peter. Let me talk a little bit about InfiniBand, the new speeds there, and actually I'm also going to talk about signaling and cabling in new speeds in ways that probably apply to all of these, or apply to multiple types of network fabrics, not just InfiniBand. So first, InfiniBand is a very low latency interconnect fabric. It supports RDMA and other offloads. For example, in some cases, it can actually process data in the network while it's moving from server to server. And it's typically used in these use cases that I've shown here, so high performance computing, artificial intelligence and machine learning, some kinds of media and entertainment, though of course also Fibre channel and Ethernet and PCIe are also widely used in media and entertainment. And then some specialized clouds, so HPC cloud or AI cloud, some of those use InfiniBand. And then data storage for just those above use cases, so connecting fast flash arrays for high performance computing or for artificial intelligence. Sometimes that uses InfiniBand as well. So in terms of speeds, what people usually have today for InfiniBand is what we call FDR, which means 14 data rate, or EDR, which I think is, I think it's extended data rate, but that means 56 gigabits a second or 100 gigabits per second, and it runs on 4 lanes. So either 4 lanes with 14 gigabits each, or 4 lanes with 25 gigabits per second each. So this EDR technology is actually very similar. If you look at the electrical signaling, it's very similar to 100 gig Ethernet or 128G fiber channel. As I'll talk about later, they use a similar signaling methods and similar bandwidth, and in some cases, for optical cabling, they often use the same optical cabling. And then likewise, the FDR rate has some electrical similarities to 64G fiber channel. So FDR and EDR from a PCIe standpoint, so Peter gave a great presentation about where we are with PCI Express. So from a PCIe standpoint, EDR or FDR was really kind of designed to use PCIe Gen 3. They use 8 lanes for FDR at the 56 gigabits a second, and 16 lanes for EDR. And that makes sense because PCIe Generation 3 with 8 lanes has a theoretical limit of, I think, about 64 gigabits a second, and FDR is 56 gigabits a second. So there's enough PCIe bandwidth to service that network speed. And likewise, 16 lanes gives you, of Gen 3 gives you about, I think, 128 gigabits a second, which allows you to do the 100 gigabit per second InfiniBand, or 100 gigabit Ethernet, or 128G fiber channel. So what's new in InfiniBand is arriving now with the hardware now in beta, but not yet GA, is HDR. HDR is 200 gigabits a second of data throughput, and it uses 4 lanes of 50 gigabits each. Or they have the option to use 2 lanes, which gives you 100 gigabits, and it's called HDR 100, because today, 100 gigabits is usually 4 lanes of 25, so this new technology gives you the option to have 2 lanes of 50 gigabits per second to get 100 gigabits. So you get 100 gigabits a second with half the number of cables or wires, or half the number of optical fibers. So EDR is really designed to use PCIe Gen 4, which Peter talked about. And the reason is that to get 200 gigabits a second, you need 16 lanes of PCIe Gen 4 on the PCIe bus. Or you can have 32 lanes of PCIe Gen 3, but nobody makes a server with a 32-lane PCIe slot, as far as I know. So the vendors have come up with a special card which can plug into 2 16-lane slots at once to get that 200 gigabits a second using PCIe Gen 3. But really what they want is a server that does PCIe Gen 4, and then that makes it much easier to get that 200 gigabits a second. So one more slide about InfiniBand, then let me talk about the sort of more universal signaling and cabling aspects. So InfiniBand is pretty much always set up as lossless. It uses credit-based flow control, which is different from Ethernet, but it's similar to Fibre channel. Fibre channel and InfiniBand both tend to use this credit-based flow control, so they make sure they know whether or not there's availability on the receiving end before they send data. But one difference is InfiniBand does not use forward error correction or FEC. So Fibre channel has added it, Ethernet uses it most of the time, but InfiniBand is designed to use higher quality cables with a lower error rate, which means they don't have to use FEC and they get lower latency. But the trade-off is, as Peter mentioned, they have to use more expensive materials. So the InfiniBand cables are more expensive than the 200, whether it's 100 gigabit or 200 gigabit, than the equivalent Ethernet cables, especially on the copper side, because you have to use this higher quality material in order to get that lower error rate so you can get away without FEC. And interestingly, Ethernet has also recently added the option to go without FEC, and again, that gives you lower latency, but it's only if you're using the extra high quality, which means more expensive cabling, and for short distances, I think only up to 2 meters. Beyond that, with Ethernet, at 25 gig and above, Ethernet expects or requires the use of forward error correction to get that sufficiently low bit error rate. So let's talk about 200 gigabit signaling, and this actually applies not just to InfiniBand, but also 200 gig Ethernet and 256G fiber channel. So there's a change from NRZ to PAM4 signaling. What does that mean? NRZ is non-return to 0, and PAM4 means pulse amplitude modulation with 4 levels, which you can see in the diagram here. So in the old way, you had a 25 gigahertz clock, and you had 1 bit per tick, either 0 or 1 for every tick of the clock. With PAM4, you have 2 bits per tick. There are 4 levels shown in the eye diagram in the upper right. And so with these 2 levels, every 25 billion times a second when the signal ticks, I can send 2 bits of data instead of 1. Whereas with the NRZ, I could send 1 bit of data. So the way we got from 25 gigs a lane to 50 gigabits per second per lane is not by increasing the actual signaling rate from 25 gigahertz to 50 gigahertz, or gigabaud, but by keeping it at 25 gigahertz, but getting 2 bits per tick instead of 1. So this ability has been added for not only HDR InfiniBand, but 200 gig Ethernet, 56 and 256G fiber channel. They all have a similar electrical signaling method in order to get this higher data rate. And the cabling, there are also a lot of similarities, at least on the optical side. So the old cabling, if you wanted 4 lanes, you had QSFP28. The new one is now QSFP56, which allows 4 lanes of 50 gigabits a second. And there's another option. There are 2 new form factors of plugs called QSFP double density and OSFP. And those 2 options, I don't have a picture of OSFP, they both allow 8 lanes at 50 gigabits per second, though I believe QSFP-DD and OSFP are still in final development. I don't think the standards for those have been finalized. So what happens when we go to these higher signaling rates? Well, someone asked earlier, and it was mentioned on the fiber channel side, but it's true for Ethernet and InfiniBand as well, the copper cables get shorter. So with 100 gigabit, when you had 25 gigabits per second signaling, and you could have 100 gigabits with 4 lanes, you could go up to 5 meters with copper. It started out 3, and then with some refinement and higher quality materials, they got up to 5-meter copper cables. Everything beyond 5 meters had to be optical. With this new 200 gigabit per second technology, the copper cables can only reach 3 meters. And then actually the question online was actually earlier, what happens when I get to the 100 gigabits per lane signaling, which is the next step we're all looking for and across all these fabrics. And it looks like, as Peter, I think David mentioned, that expected copper cables are probably limited to 2 meters at most when we get to that 100 gigabits per second signaling rate. So that is the next step, 50 gigahertz signaling, which will be 50 billion ticks per second, but 2 bits per tick, so with PAM4. So that will allow 100 gigabits per second of information per lane. 4 lanes will give you 400 gigabits, and if you can do 8 lanes, which you might be able to do with these special new plug formats, or transceiver formats, then you could get 800 gigabits per second of data throughput. All right, here we have some pictures showing that QSFP56 is sort of backwards compatible with QSFP28. You can plug the older, slower one into the new slot, but you cannot plug the new QSFP56 connector into the older QSFP28 sockets on a switch or adapter. And then there's standards for the 8-lane QSFP or 8-lane OSFP plug. So there are 2 standards that are sort of fighting it out now on who's going to be the winner for carrying 8 lanes. So that's done with my section. And by the way, someone said they lost audio. If you refresh your browser or re-enter the webcast, then you should regain audio. So there's one summary slide, as I would say, faster networks are here. You can get more bandwidth when you need it. They'll let you support faster servers and storage. To have more efficient large fabrics where, again, faster uplinks between switches let you have fewer switches and more efficient, less costly networks when you're linking lots of switches together in a huge fabric. Most customers are only going to deploy these faster speeds where they need it because the faster speeds cost more money. So it's very possible that to the desktop and the Wi-Fi you'll have 1, 2.5, and 5 gigabit per second Ethernet, and then regular servers will be running 25, 50, and 50 gigabit Ethernet or 32G and 64G fiber channel, and then the really fast flash arrays or the fastest GPU servers will be running that 200 gigabit Ethernet, 256G fiber channel, or HDR InfiniBand, all of which can do about 200 gigabits per second of throughput. Because it doesn't make sense to pay for the really expensive connection to a server that doesn't need it or to a desktop that can't use it. Also, as you go to these faster speeds, you must match the PCIe bus bandwidth. Basically, the PCIe bus or the slot has to be capable of feeding that data, whether it's inbound or outbound, to the different faster networking technologies. So I talked about that earlier. And the good news is that all the network fabric vendors, including all the vendors on this call, and the CPU vendors and the flash vendors, are all working on supporting PCIe Gen 5 so that when the need for that extra bus speed is there, they'll be able to use PCIe Gen 5 as needed. All right, so before I talk about the more webcasts, we do have one unanswered question. And so let me send that question, I think, first to David and then possibly to Craig and Peter. The question is, so what do you see as the most prevalent LAN speed today, and what do you see in the next year or two? So maybe David, could you take that first, and then Sure. Craig, and then Peter?
Yeah, that actually depends a lot on the application area, which is one applications for Ethernet. So in, say, industrial and IoT applications, probably 100 megabit to 1 gig are the most common today. In automotive, again, still 100 megabit and 1 gig because Ethernet's fairly new. For in-vehicle networking, in the corporate LAN, if you still have a PC that has wired Ethernet in it, it's still generally 1 gig, although 2.5 gig and some 10 gig is there in the corporate environment for end device patch. Of course, when you have a large network, the data stations like a PC is different than what's up in the higher speeds tend to aggregate the whole network together. So in corporate LAN, where individuals may be connected at 1 gig, you'll see 10 gig, 40 gig, up to 100 in the backbone of that network. In data center and server networking, 10 gig is there's still, surprisingly enough, there's still quite a bit of 10 gig around in servers, but 10 gig is the biggest piece of the pie shipping today, and 25 gig just getting started. And it depends on the application. There's some use of up to 100 gig in servers today, but the volume is 10 gig moving to 25. And then hyperscale and service provider areas, again, for the individual server connection, it's probably 10 moving to 25 and a little bit of 100. And in the backbone and in the data center interconnects, it's more of 100 gig moving up to 400 gig.
David, thank you. Craig, can you comment on this?
Sure. Yeah, so for Fibre Channel, there is still a lot of 16 GFC out there, the reason that we still see a lot of the slower speeds is, as with the other technologies, there's a lot of backward compatibility capabilities. We are seeing some uptake of 32 GFC, and especially with this all-flash arrays, that's starting to accelerate. And with 64 GFC this year, we expect the all-flash array data centers to start pushing that as well.
Great. Peter, any comments about what is the most prevalent LAN speed you see?
I can't comment on LAN speed, but I'll comment on PCI Express. So today, by far, it's all Gen 3. Some people have production Gen 4, but we really expect to see that ramping in 2020. And Gen 5 will probably be out in 22, 23 in production volume.
Okay, that makes sense. And actually, David, back to you with another question about Ethernet. What are the maximum cable distances for 2.5G and 5 gigabit Ethernet?
In general, so as I mentioned earlier, 2.5 and 5G base T were specified to take advantage of the installed base of cable, which is predominantly Cat5e and Cat6. So both of these speeds can reach up to 100 meters on both Cat5e and Cat6. There is a little bit of gray area in the 5 gig on Cat5e, in that if you have tightly bundled cables or some other source of interference, that might reduce your 5 gig reach on Cat5e. But there are guidelines written on how to test your cables and how to make interference. So that's the one case that may take a little bit of work and a little bit of thought. But in general, the way wiring is dispersed around, say, a corporate office space, the wires are tightly bundled at one end where it leaves a switch perhaps, and then they fan out through the rest of the office space. So that tends to naturally reduce the cross. So in general, 100 meters reach for both 2.5 and 5 on Cat5e and Cat6 is achievable. And of course, if you have a newer office building that already has Cat6a, then of course 100 meter reach is easily achieved with all speeds up to 10 gig.
Okay, great. And I'm going to come right back to you with another question. It's will FEC, forward error correction, be available for Ethernet networks in automotive uses, and will it be needed inside the car?
Yes. So some of the forward error correction has been in some flavor of Ethernet for quite a while. Actually, 1000 base T uses forward error correction. 10G base T uses a very strong forward error correction. It's more in the optical space or the direct attached copper space where FEC is new. And yes, the automotive Ethernet flavors, especially as we're trying to get up to higher speeds. Again, what's being specified now is 2.5, 5, and 10 gig over the single pair cable, and soon to work on 25. And yes, they do use forward error correction.
Excellent. All right. So that's great. And so I have a question for the panel, and then we have a few minutes left, and you can take it. And then the question is, what do you see as driving people moving to higher speeds? I talked about for one slide, but one brief slide, but really what's causing people to need, or where are they going to need these higher speeds, in data centers? So maybe let's start with Peter on this.
Yeah, I mean, for PCI Express, obviously higher performance networking, and I'll let the others speak to applications that are driving those. But in addition, it's connecting accelerators, GPUs, and very high performance NVMe SSDs that are driving the performance requirements. So we've been at Gen 3 for quite a while, and there's certainly a need for faster interfaces. So with Gen 4, as John pointed out, people are cabling 2x8 to get by 16 bandwidth. So faster networking, AI, GPU accelerators, and faster NVMe are driving the increases. Okay, great. Craig, what about on the fiber channel? Well, you don't have to talk just about fiber channel, but you mentioned that the all-flash array, FC NVMe, those are two drivers of higher speeds. Do you see anything else or any other comment on what's driving the need for these higher speeds?
Well, I think some of the same things that Peter just mentioned in terms of the AI and in particular, and then data mining as well, and then in enterprise are things that are still driving these high speeds. And some of the cloud applications as well are starting to drive these high speeds for these large cloud data centers.
Okay, makes sense. And back to David, any thoughts about, any last comments? I know we've talked about it already, but comments about what drives the need for higher speed networking?
Yeah, so ideally, say take a data center or a server style of application, ideally we always have the perfect balance of compute power and interconnect or networking bandwidth and memory capacity that fits the application that's going to be run on it. So the types of applications that we're running in servers and data centers now has been evolving significantly over the past decade or so. And a lot more of there's a lot more communication involved between systems in a lot of these applications. Picture just a search engine. When you type in a few letters in your search screen, that search gets highly parallelized and farmed out to hundreds or thousands of machines. And so the ability to move all that data around and get them back really drives need for network bandwidth. Also, we may have heard the term scale up versus scale out. So if you have a compute-intensive application, you're doing genome sequencing or something, typically for compute-intensive applications, what gives you the best performance is just to have as much local RAM as possible. And of course, so now we see non-volatile memory also being approaching the speeds and the locality of what has always been RAM or DRAM. So when you have a lot of local memory connected directly to your CPUs, you're going to get the best access for compute-intensive large databases. But eventually, you run out, there's a limit to how much memory we can put inside one machine, and although that's growing rapidly with non-volatile memory, once you spill over to that point, then you start clustering and spreading your database out among multiple machines, and then again, networking interconnect becomes more important. So it's been evolving over the years with different applications, and as storage gets faster and CPUs get faster, the network has to get faster to keep up.
Well, I definitely agree with that, and that's a good point, that distributed or scale-out applications may drive the need for faster networking. Let me do the closing slides, and then there's one more question. I think we'll be able to squeeze in that last question. So I just want to point out that from the SNIA standpoint, there are more NSF webcasts coming up, and you can see all our previous webcasts on demand if you go to snia.org/forum/NSF/knowledge. Actually, it's a typo. It's NSF, not ESF now. But anyway, if you go to the snia.org website, you can find all our old webcasts and see them. Some of them are actually also available on the SNIA YouTube channel. Our next live webcast is coming up on June 18th, so in just about 3 weeks, and that's Introduction to Incast Head-of-Line Blocking and Congestion Management. That's a little bit more of a technical topic. It's not the networking 101 topic, but if you're interested in that, please register at brightalk.com. There's a link here, and you can also search for it on BrightTalk. And that would be very interesting for those of you interested in either avoiding or detecting or dealing with congestion on the network. Okay, so we do ask, before I get to the last question, that you rate this webcast. In BrightTalk, you can give us a rating. Of course, we hope you'll give us a good rating, but tell us what you think, good or bad, and give us some feedback. Tell us what we did right, what you'd like changed. As mentioned earlier, the slides for this webcast will be posted right after this live webcast ends, and the webcast will be available on demand as well. And you can find them at snia.org/forum/NSF. That's the correct URL, /NSF/knowledge/webcast. The Q&A for all these questions, I think we've gotten to all of them except one so far, will be published in the blog in probably about a week, and you can follow us on Twitter. That said, we're just about at the hour, and let me pose the last question here, and we'll see who can answer it. It's a question about, can you use, and I should know the answer to this, but I apologize that I don't. What about using active copper cables to get a bit more reach over passive copper cables? Can you use active copper cables to bridge that distance between passive copper and then before you go to optical? So let me see if we can start with Craig. Can you take that question? Otherwise, we'll pass it to someone else.
Yeah, and then that's definitely possible. It comes down to a cost power issue. You may reach a point where the active cable costs more than the optical cable, and then it's not really worth using it. Right now, for longer reaches, optical cables are ideal because they have a lower cost versus some of the active cables. Plus, they have no extra power requirements.
Got it. That makes sense. David, did you want to add anything to that answer?
Sure. Yeah, the active copper, fits in this window of, as we mentioned, as we go to higher speeds, the passive copper reach gets shorter and shorter. So active copper kind of has a bigger space to play in as the passive copper reaches go down. But from the host port's view, whether an active cable is copper inside or optical inside, the host port host same electrically. So it kind of is an implementation choice, and from one feed generation to the next, see which one happens to be more popular in the market. Let's say that back in 10 gig, there were copper cables around, but if optical seems, this isn't with any market data here, but just my perception that active optical seem to have a little more market than active copper. But I think as we go to higher speeds, there's a little more of a where active copper is going to be interesting. I've also seen some products coming out. They're going to do some things. So as we talked about earlier today, we've got different signaling schemes, different forward error correction or coding within the physical layer itself. And something you can do with active copper cables in the near future would be, say, to take a 400 gig Ethernet port that's based upon the newer 50 gig PAM4 signal and break it out with gearbox in the cable assembly itself that can break out a 400 gig port to the legacy 4x2500 gig ports and help gap between the technology generations. So if you buy a 400 gig switch, you can use it with the prior generation 100 gig. So there's some interesting things coming on with active cables that I've seen.
David, thank you. You were breaking up a bit there at the end, but I think that's a good point that you can use the right kind of copper splitter cables to split out, or it's also available in optical, I think, to split out a newer generation faster connection into two or four of the older generation slower connections. And I think we should mention, right before we close, we've just got about 3 minutes over, but the interesting thing is when you go to these new speeds, whether it's Ethernet or Fibre channel or InfiniBand, usually you can reuse the existing optical cable. You do have to get new transceivers, and if the copper cable has to be usually replaced with newer copper cables, but you can typically reuse the existing fiber optic cable plant even as you go to the faster speed. So that's a part of the great thing about going to these faster speeds. You can usually reuse the existing fiber optics that are there just by switching the transceivers out at the ends. Okay, so we've gone a bit over. Thank you, everyone. Again, I'd like to remind the audience, we do love to get feedback and ratings on it. If you don't mind, please do that. There was one more question, but we've run out of time, so we'll answer that. It's a good question, but we'll answer that in the FAQ that'll be published in our blog. I'd like to thank all our wonderful presenters and thank everyone in the audience for attending. If you liked it, refer your friends. They can come back and watch it, not live, but watch it on demand afterward as well. So that said, again, big thank you to everyone, and that concludes the SNIA NSF webcast about the next generation of networking speeds. And this is your host, John Kim, signing off for today, and I'll see you all on the next webcast.